Hello, everybody. I'm sorry I cannot be with you today, but I'm at an important meeting. I'm glad to be there as well. Wish I could be with you and be there at the same time, but I can't do those kind of things yet. So I am going to try to be here with you virtually. I'm sure you're excited about all the screen time you're getting. I hope the movie about the law of inertia was good. You should make sure you take a few minutes and compare answers with each other to make sure you have it the way you want it. See what you can learn from that. And then turn that in to your substitute teacher, please. And then make sure that you have one of these worksheets. We'll talk about worksheet 2 here. Um, and this is a chance for us to take the stuff we've been working on, we did on Tuesday, plus the worksheet we did yesterday, and put it all together to start solving more complex problems. So let's get started. The first page of this, it shows a force that's at an angle. We've talked about forces at an angle now. We know that they are really a combination of over and up. So what you're being asked to do here is draw the original angle there, and then you're going to put the angle in here, draw the over part, the up part, and then determine the values for these two. As you remember, this will be sine of the angle times the original force, which is 12 newtons, and then you'll have the strength of the upward component of that diagonal force. Down here, you'll have cosine 60 times that 12 newtons, and that'll end up being your force in the x direction. So you can take a few minutes and work together to get all these worked out together, just for some practice, no big deal. Okay, so once we've figured all that out, let's scroll down to the next page, because here's where I think is a little more challenging, and this is where it becomes important. Not that it's not all important, but this is where we're putting it all together. So here you've got a situation where we have a person that's pulling on a desk. So if they're pulling on it, notice that their arms are pulling diagonally. So we're going to have to employ the skills that we mastered up here to break these things into equations or into components and then put them into equations. So the first thing we're being asked to do is draw a force diagram for the desk. So like yesterday, let's represent the desk with a dot. Then we've got to think what's going to be there. What's always there? That's right, gravity. Good job, guys. Okay, there's the other half of that arrow, and we will label it accordingly. So the question we always have to ask ourselves is what else is touching the desk? Well, we know the ground is touching the desk, so the ground is going to be pushing up. So here's tricky business. Is that normal force given by the desk going to be equal to gravity, greater than gravity, or the same as gravity? And I'm not really sure right now, so let's just draw it up there and then we'll change it later if we have to, once we figure out what's going on. Because we know that person is pulling diagonally, so you've got this deal. If the person's pulling on it, what do we call it when somebody's pulling? That's right, it is a, oh my gosh, I'm gonna freak out. It is a tension force because there's pulling. Yes, there's a human on it, but let's assume that the arms are like a rope or a cable in this force. So there's a tension there. This is tricky because what we want to be able to do is compare the up and down forces to the back and forth forces and see if we can make equations. But this diagonal is going to give us some problems. So we need to reflect back upon what we did here. Whenever we have a diagonal force, we need to resolve it into x and y vectors. So what we need to do is take that diagonal and break it into an over and an up. And we're going to call this f of t, the tension, but in the x direction. And we're going to call this up one f of t in the y direction. How do you feel about them apples? A little ugly? Because what we can do from all that is we can then figure if we have this diagonal vector broken into an over and an up, what we do then is just get rid of that diagonal vector, and it cleans things up for us a lot. Oops, didn't mean to do that. Didn't mean to do that either. But we end up with, so we end up with a boiled down situation like this. And this is convenient because there's no more ugly diagonal that we don't know what to deal with. Now everything is nice and back and forth and up and down. And what we can do is we can take this guy and we can move it over here and just pile them up. F, T, Y. And now everything is moving in the same direction. We can clean this up a little bit, do this. So now you can see the reason we did this is this diagonal force, which was represented here diagonally, is now just shown as the x part of it and the y part of it all pulling on the same dot in the middle. Why do we care about that? Well, because it lets us do B, C, and D. So B says write an equation that describes the forces which act in the x direction. So those are going to be these. So here we're going to have the net forces, which is all of them, equals all the forces added up. It's going to be the frictional force, which is here, plus force of tension in the x direction. How do you feel about that? All right, there's your equation for the x, and these are forces in the x direction. Now we're going to do the same for the y. The net force, all of them added up, in the y direction equals, well, what forces do we see? What do we see there? Oh, we see which this would move for me. Not that much. Okay, we've got the top one, which is F, force of tension in the y direction, that's the very top, plus the normal force, that's this guy here, plus gravity. Those are all the forces. So all you gotta do is just write an equation. That is it, my friends. And then we're gonna come down here a little bit. And now it says determine the x and y components of the force of tension. So now what you can do, you can go back and do the math that you probably already thought about. Do we know? What do we know? They have a 200 Newton force acting at 30 degrees above the horizontal. So you can do your SOHCAHTOA here and you can get that all worked out. Please do that now. Then what you can do is figure out what's going on for these. You have to solve them. And here's the key to all this. The desk does not budge. The desk does not move. So what does it tell you about the forces that are acting on this desk? That means the net force must equal 0. Everything must cancel out. So what that means then is that we go to the y part, or the frictional part, which is in the x direction. We know that F net equals the frictional force plus the tension in the x direction. And because the net force equals 0 and the net force equals the frictional force plus the tension force in the x direction, we can combine them and say that 0 equals FFR plus FT in the x direction. You've solved for the tension force. You did that up here. So you can use that to solve for the frictional force. There you go, folks. What do you think of them apples? All right, practice that. Rewind this video. Do what you got to do. And then I need you guys to jump in and do everything you can down here. I'm not convinced that there's enough room on this worksheet for you to work things out. I think you might be better off doing this on a clean sheet of paper where you can spread out and really see your work. When you're done with this, if you finish, please grab a copy of worksheet 3 and do what you can with that. Okay, so treat each other nicely. Everybody love everybody. Be nice to the substitute teacher. Do what you can. Make something positive come out of this day. And I look forward to seeing you tomorrow. Bye-bye.